So thank you so much for joining this paper and R&D session. And today, so my name is Nobuaki Kubo from Tokyo University of Marine Science and Technology. And okay, so today we have 9 papers on the website, and actually in this session, so we have, so each speaker has 15 minutes, and actually only 15 minutes, which means 12 or 13 minutes, and further 2 or 3 minutes are available for question and discussion, I hope. So, okay, so maybe may we start the paper and the R&D session now? So first speaker is Mr. Omar Hamol Ali. No, he is not here. He is not here. Just no. So Mr. Omar Hamol Ali, maybe he is not here. Okay, so okay, next speaker. So next speaker is Mr. Dr. Rui Hirokawa-san, so from Mitsubishi Electric Corporation. So I guess he's here.
Okay, hello, I will share my screen.
Thank you, yes. Please start, yes, please, yes.
Okay, so can you see my screen?
Yes, I can see. It's right, yes.
Okay.
We can see.
Hello, everyone. Hello, everyone. My name is Rui Hirokawa, working for Mitsubishi Electric Corporation, Japan. Today, I will introduce early stage result of PPPRTK demonstration in Thailand. This is a joint research project with Chulalongkorn University. So I would say, at first, I would say thank you for my co-authors. And please note that this is a purely academic research result. So it is not currently related to the QGSS project itself. This slide shows the contents of my presentation, including 4 topics. First, I would say I will introduce QGSS project. It is background of my our research. And then I will introduce PPPRTK demonstration plan in Thailand. And I will show you the very early result of PPPRTK portion near the Bangkok, and conclusion. First, I will introduce QGS syllabus. This is PPPRTK service for Japan. It was operational November 2018, so it is now past more than 3 years of operation in Japan. And this is I believe it is the first satellite-based open PPPRTK service in the world. And the QGSS syllabus provides centimeter level accuracy in a minute. So convergence time is less than 1 minute. And the figure shows the structure of QGS syllabus. It is based on the Japan course network named as GeoNet, and we're using more than 300 different stations of GeoNet, and the real-time measurement is corrected by master control station, and the PPPRTK correction data is generated in real time, and it is broadcasted from the QGS satellite using QGS L6 now with 2000 bits per second. Next slide shows the specification of QGS syllabus. it's supporting multi-GNSS satellite collection, including GPS, QGIS, and Galileo. And it covers all territory of Japan. And the positioning accuracy target for static mode is 6 centimeter horizontal, vertical 12 centimeter. And the kinematic mode horizontal accuracy is 12 centimeter and vertical 24 centimeter. And the convergence time is 60 seconds, 95%, including time to receive correction data. It is estimated as 30 seconds in the worst case. And the next slide shows the performance of QGIS since November 2018. And the x-axis, the left part is horizontal and vertical accuracy for the each month. And the first year, 2019, was orange. So it has a peak on the summer season because of ionospheric disturbance, but it is improved after the improvement work to end of 2020, and the performance was improved to the 3 centimeter on average on horizontal. And for convergence time, it is also the same tendency. It has a peak on summer season, June or August, but it is fairly improved after the upgrade. And currently we have 35 seconds on average of convergence time, including time to receive correction data of 30 seconds. So in effective time to convergence after the receiving correction data is just 5 seconds. So it is somewhat like instantaneous convergence like RTK. Next slide shows the concept of SSR, space representation. So the GNSS error model is represented by multiple error sources like satellite orbit error, clock error, and satellite bias. And for atmospheric part, it includes ionospheric delay, tropospheric delay. And these conventional TK in our OSR domain correct such whole error as a lens correction. And the SSR approach, we estimate each error sources and send to the user for each byte states. And we are considering the dynamics of each error sources. So orbit error, for example, is slowly changing. So the updated rate is slower than clock correction. So by using such technique, we can compress such data stream by 1 to 1,000. So 0.1% compression ratio could be achieved. And the PPP-RTK approach, we use broadcast all of the error sources, including atmospheric correction. And the other side, PPP correction, just broadcasting satellite part correction. So convergence time, it could be different. And the convergence time for PPP-RTK is less than 1 minute. And the typical PPP for PPP is around 30 minutes to 15 minutes. And the coverage area, scalability is higher for PPP, and it can easily cover global correction. Next slide shows typical position result in real time for the low-cost, high-performance GPS receivers, such as the Block F9P. Recently, F9P is natively supporting receivers. It is one of the examples on last December. On one day, it proved very accurate result. It has 3.3 centimeter, 95% in real time. And this receiver is already a very low cost receiver compared with survey grade receiver. So it can be applied for many kind of application. Next slide shows the typical application of QGIS, including ADAS. It's Nissan earlier recently available electric car is using QGIS Silas. And the other applications, such as agriculture, seaport application, automatic docking, and the drone application is developed in Japan. Next slide shows the high accuracy GNSS positioning service in other countries. This chart table shows the recently available open satellite-based high accuracy GNSS correction service. Former day, this service was provided as a commercial service, but recently many GNSS providers start to provide such kind of open service. So it includes QGIS Silas, and the QGIS Madoka PPP is also in development. And the Beidou 3 PPP is already started in 2020, and the Galileo HAS will be started currently in test phase. And the Australian and New Zealand service will start soon. And GLONASS and Korea KPS is currently planned to have such high accuracy service. So many kinds of services will be available. So interoperability and the standardization of format will be very important. So we proposed the open format named as compact SSR. It's a highly efficient format for PPP and PPP-RTK. And it is the derivative of this format is already applied for other service, such as Galileo HAS and Beidou, also using the derivative of such format. And it is also applied for the standard of CGPP as a 5G standard. So next section shows the PPP-RTK demonstration in Thailand. So in Thailand, over the 200 GNSS station is available, but currently it is operated by 5 different national agencies like RTSD or DOL. So currently national data center will be planned to be established, and it will be operational in this year. So connectivity and stability could be improved, we hope. So for the first stage of demonstration, such kind of national data center is currently not available. So we connected, we have at first on the stage, we planned 3-step approach for demonstration. The first step will be using small network near Bangkok. We will demonstrate real-time generation and post-processing analysis in a static mode. This is the first stage. And next stage and third stage will be use wider network, hopefully cover a whole Thailand network, and using kinematic mode analysis. So I will show the initial result. The first demonstration was conducted on a small network near the Bangkok, using around 10 stations, using a DOL, HII, RTSD stations. So that dot shows the position of stations near the Bangkok. And we performed the analysis using RTK software. And next slide shows the system configuration. So using the Thailand coordinate station real-time stream, we received the LTCM MSM stream for the measurement, and we generated SSR correction data in real time in a server located on Chulalongkorn University, and we integrate SSR correction, and we also generated compact SSR in real time. And the portion result is processed in post-processing mode in the RTK leaf. But it is processing algorithm is purely compatible with the real-time mode. And we sent the compact SSR as in a table, and we also sending grid definition mode is compatible with CGBP to know the position of correction point. So this is a concept of grid definition. It is already in Japan, QGIS, it is described in ICD, but in 3GPP, for the generalization of collection service, the grid point could be sent to the in the collection stream. So we defined two type of grid point. It is already defined in 3GPP standard. In that stage, we use type 2 grid point definition because it is very simple. So this is our result of our portion using CUUT reference station. It is 1 hour result, and it proved the almost centimeter level accuracy. It proved the 3.3 for east and 3.4 for north relation, and it proved the instantaneous conversions after just receiving correction data. So this good result. But we have planned to have more longer time result if a stable connection for the national data center is available. For the summary of conclusion, we demonstrated PPRDK service in Thailand, and the initial performance is evaluated, and improved the quick conversions in the high centimeter level result. And currently we have some stability issue for coast connection of coast station and the limited visibility for QGIS and Galileo. But I hope we can it could be improved. And once NSCDC is available, we will. I hope we can start the evaluation on a larger area. So thank you very much. And at last, we would like to thank you to RTC, SD, and DOL and HII for sharing the data using in this initial study. Thank you very much for attention.
Thank you very much. Thank you very much for very interesting presentation. It covers a lot of things in PPPRTK, yeah. So, okay, so maybe we can have 1 or 2 questions. So do you have any questions from audience? Okay, okay. So maybe after this, in the last of this session, so maybe we can have some questions from the each speakers. Okay, thank you so much for Dr. Hirokawa.
Thank you.
And, okay, thank you. So the next speaker is Mr. Satoshi Kawamoto-san from Geospatial Information Authority of Japan. So the title is Recent Advances of GeoNet, a dense GNSS coast network of Japan. So Kawamoto-sama,
hello, can you
yes.
hear me?
Yes, and
I show my slide. Can I share my slide? Please close yours. Oh, okay. So can you see my slide?
Yes, yes, I can see slide. So please start. Yes.
Okay. I'm Satoshi Kawamoto from Geospatial Information Authority of Japan. My talk is about recent advances of GeoNet, dense GNSS quartz network of Japan. Firstly, I'll show the overview of GeoNet. GeoNet is official governmental GNSS network in Japan that consists with over 1,300 stations that covers whole Japan with about 20 kilometers spacing. The main purposes for the network is surveying and mapping and monitoring of cluster deformation, and providing the location-based services. And now the network is capable of GPS and QGSS and GLONASS and Galileo.
川本さん、すみません。次のスライドの分まで見えてますけど、よろしいですか？いや、別にね、これでも全然綺麗に見えてるんですけど。
sorry.
どれだろう？まあ、行きましょうか。
Is it okay?
まあ、いいです。OK です。行きましょう。
Sorry. So now GeoNet is operated continuously 24 hours, and 1 Hz real-time data are streamed to analysis center with GSI and broadcasted to various users. And the data are archived and provided to users in various fields. Linux data for post-processing purposes for surveys and mapping, and site coordinates of GeoNet are also provided and used for monitoring of cluster deformation. And real-time data are used to serve precise real-time positioning. This is called location-based service and used for ICT construction and precision farming, and also used for QGSS, centimeter level augmentation service. And recently, the data also used for the weather forecast because the observed GNSS signal contains tropospheric delay information. And this is an example of the GeoNet station located in the headquarters of GSI at Tsukuba. The station is made of stainless pillar of 5 meters height, and the GNSS antenna is fixed on the top of the station and covered with radon. This is because it's rainy climate in Japan. And the GNSS receivers and other devices are stored in the station itself. There are also batteries to continue observation when sudden power blackout occurs. And there are several types of good GeoNet stations. The older models are single tube stainless pillar, but the latest type adopts dual tube structure to prevent thermal expansion. The thermal expansion effect sometimes up to 1 or 2 millimeters. So this type of stations are more precise. And the number of stations of GeoNet has been increased for the past 25 years. The previous two networks called Cosmos C2 and Grapes consist of about 100 stations, and they were integrated to GeoNet. And currently, GeoNet became a dense GNSS network supporting increasing users in various fields. So this, and especially application for location-based services is increasing now. Location-based services based on GeoNet are used for various purposes. For example, smart farming, ICT construction using wireless services. These pictures are examples for them. The left one shows automated agricultural machinery, and the pictures on the right shows machine guidance and control in ICT construction. So now GeoNet is important infrastructure for precise positioning in Japan. And next, I show some advancements in GeoNet analysis. The first one is new daily site coordinates called F5. The daily site coordinates of all GeoNet sites are calculated and provided for long years. The daily site coordinates are used for monitoring of cluster deformation in Japan because Japan is located on very active plate boundaries. This solution is also used for precise positioning to correct the cluster deformation effect in Japan. The analysis strategy has been updated several times, and the latest version started last year, April 2021. The new analysis strategy is called F5 solution. The F5 solution provides daily coordinates of all GeoNet stations for period. The coordinates are aligned to ITRF 2014. And to keep the consistency with ITRF, we use global analysis to realize. And the Bernese software version 5.2 is used for the analysis. And we use the latest mapping function VMF1 for the analysis. And the F5 solution shows a very good precision below 3 millimeters for horizontal components and about 7 millimeters for vertical components. The F5 solution shows also very good agreement with the IGS solution that it's the IGS realization of ITRF. The blue lines in the time series show the differences between F5 solution and IGS solution. There are very small bias between them. That is the order of a few millimeters. So this F5 solution is now a basis of the monitoring cluster deformation in Japan. And the next advancement is the development of the real-time analysis system for the GeoNet. A GNSS real-time analysis is very important information for the disaster prevention. It provides displacement field caused by large earthquakes, and we can also estimate magnitude and for the model for the earthquake rapidly. These figures show the real-time displacements just after the 2011 Tohoku earthquake. And the maximum displacement occurred for more than 5 meters. This displacement data free from the saturation problem occurred in seismometer data. So again, GNSS real-time analysis can provide important information for earthquake disaster prevention. So we, GSI, developed the real-time GeoNet analysis system named the Regard system. We started the development of the Regard system after the Tohoku earthquake in collaboration with Tohoku University. And now Regard system is already working and provides real-time displacements caused by large earthquakes and also moment magnitude and for the models. So I show some examples for the Regard system. The first example is a simulation result for the Tohoku earthquake. The figure on the left shows the vectors calculated by the Regard system, and for the models, automatically estimated by the Regard system. So as you can see, the large displacement vectors were estimated, and also the photo slips indicated offshore of the Tohoku. So real-time displacements and finite photo models were estimated successfully, and accurate moment magnitude of about 9.0 was estimated in about 3 minutes. And the next example is the case of the 2016 Kumamoto earthquake. This is not the simulation result, but the real result that the Regard system worked in real time. The Kumamoto earthquake occurred in the western part of Japan, and the main shock of moment magnitude 7.3 caused significant damage around the focal area. the earthquake was right-lateral strike slip along the Futagawa-Hinagu fault zone, shown by the red line. The regard system estimated large displacements caused by the Kumamoto earthquake. This is a real figure released on our website after the earthquake, and significant horizontal displacements up to about 1 meter were observed around the epicenter. And then finite fault model was also estimated automatically by the regard system. These red lines on the figures show the automatically estimated fault models, and that was converged within about 5 minutes and estimated along the Futagawa fault with a moment magnitude of 6.96. So this result was agreed well with the other post-process fault model estimated from GNSS and INSAR data. This result demonstrated the real performance of regard system. And currently, the results of regard system are used for several purposes. The displacement data estimated in real time will be provided via our website and also provided to governmental committees that evaluate the earthquakes. And also the finite fault model and the magnitude estimated in real time are used for rapid tsunami simulation. And future improvement regard system includes the use of QGSS satellites. We are now evaluating the effect of QGSS satellites for real-time positioning. This shows a preliminary result, and it shows improvements in positioning result. Current accuracy of positioning time series is shown in red colors, is about in the range of between 2.5 or 3 centimeters for horizontal components. And if we use QGSS, that is shown in blue color, the accuracy was improved to about 2 centimeters. The improvement was also found in vertical component. This is our future work, but QGSS is one of the key to improve our system. And then more accurate displacements and fault models could be provided. And I summarize my presentation. GeoNet is a dense quartz network of Japan that is used for various purposes. And recently, the application for the location-based services are increasing. And the recent advancements include updated daily solution F5 and the launch of real-time analysis system regard. And the future improvement includes the use of QGSS, but this is our future work. That's all. That's all. Thank you very much.
Thank you very much for interesting presentation for Japanese GeoNet and also regard system. So from audience, so we can have 1 or 2 questions. Do you have any questions from audience? Does the regard system has web portal? Is it freely accessed? 川本様、チャットの質問、はい。
No, currently it's not provided on the website automatically. After we check the result of the regard, and then we provide it on the website. So yes, that is the future, one of the future works. Thank you.
Thank you. Okay, so do you have any questions? Maybe one question.
Excuse me, there's a few questions from the participant.
Okay.
May I read the first question? What is the time resolution update rate of IONO correction? Which day are your results based on?
IONO collection.
Oh, I'm sorry.
So
this question is for my presentation or the current presentation.
Hirokawa, please.
Okay. So can I answer my question? This question or later?
Would it be possible to answer the question right now?
Right now.
Okay. So the update rate of answer correction is 30 seconds. And the what is the second question?
Which day are your results based on? I think they asked for the time resolution of the IONO collection, and then which day are your results based on? I think when did you come up with the result?
Okay, so last June 2021, it's a day of the year 205.
Thank you. And there is one more question for Dr. Kawamoto. Does Regard system has web portal? Is it freely accessed?
Currently, no. Currently, no. We are providing the limited users in the government.
Thank you much for answering the question again.
Okay. Again. Oh, okay. Thank you. Thank you for your questions. Okay. So Kawamoto-sama, ありがとうございます。Thank you. Thank you very much for your presentation.
Thank you very much.
Okay. So next. Okay. The next speaker will be Mr. Mohammed Nur Kayali from Geo ITS. I guess.
Yes.
Yeah. Okay. Thank you. Thank you. Okay.
So the time is 4 p.m. So still 15.
Okay.
My turn is in the 4 p.m. I'm right?
Yes. Right now.
Okay. Good. Yes. Okay. Sensei.
Okay. Thank you. Please start.
Okay. Yes. No. It's my turn or no? Hello? Is it my turn?
Yes. You can start your presentation. I can see
yes.
your slide. I can see your slide very clearly. Yes.
Okay. Yes. Okay. So today I will present about the low-cost GNSS receiver performance for volume calculation and horizontal frame network in Indonesia. So next, so this is my outline, preliminary and data and location, result and analysis and conclusion. Okay, so this is the background that we usually use topography for determine position and between horizontal and vertically, and also in this case we calculate volume after we get the position in horizontal and vertical. Okay, next. And we also have some problem with a geodetic GPS about the high pass, and we also have some development manufacturing for low-cost GNSS only the on-board, and this is very good if we compare to the volume calculation. Because the on-board only GPS is cheaper. It's only 200 and 300 euros. Okay, next. Then we will make RTK GPS on board using Ntrip and compare with GPS geodetic for volume calculation. Then we will make some analysis using statistic. Then compare also using total station. So as we talked that we compare local GPS and geodetic GPS, then compare again with the total station for cut and volume measurement. Okay, please. Next. So in this case, we will have some profile and what the difference about the result between two methodology. Okay, please. So this is our methodology. This is the area of the location about 2 hectare, 5 point, yeah, in Indonesia. Okay, please. So we use TopCon for total station, and then we use Comnav 300, and we use onboard K70 and versus PX316. This is the figure. Okay, please. Next. So this is we compare all this situation and make the conclusion. Okay, please. So this is processing result. It is for quite good, yes, for total station, and this is the corrected height and the standard value that we will use in the observation. So all value is compared to this result. Okay, please. So after we compare, it's quite good. Yeah, between geodetic GPS on board and then total station is quite good. And then please, this is for horizontal correction about 6 millimeter in average, yeah, or the RMS error is around 13 centimeter. Everything is quite good here in the horizontal network. And then please, and this is for cut and fill. So we have a little different in the volume. We will make some figure for the volume, for cut volume and fill color. Yes, please. We also make AutoCAD. Yes, and Excel mean we use our formula by ourselves. Okay, please. And this is some 3D modeling volume for calculation. And then from the total station measurement for 3D modeling GPS measurement using PX300. This is low-cost GPS. Okay, please. This is another low-cost GPS compared with 3 Comnav, yes, by 300 Comnav measurement is quite good also. And then please. This is analyzing of processing result using different volume about -2 about from 12 until 31 meter cubic, or around the biggest one is 0.7%. Okay, please. Yeah, so conclusion. So in this case, everything we have concluded that the low-cost GPS is still have some promise to develop, even using a very cheap module. Okay. Then this is some measurement documentation using our equipment. Okay, thank you very much. Okay, Sensei.
Thank you. Thank you very much for your presentation. So since I am not a surveyor, so I am not so familiar with TS, but anyway, so sorry. First of all, I have two questions. So I have one common receiver. So you showed two common receiver, K708.
Yes.
And the T300. Okay.
Yes. Yes.
Okay. So which is low cost? K708.
There is. I will. This one. Okay.
Sorry. So could you tell me how much is K708? Yeah.
So this is a low cost. This is about maybe.
Could you tell us about US dollars?
Yeah, $500.
100. 500.
Yes, and this is $700 US. Yeah. And if we compare this, this is maybe maybe this is $3,000 US.
Yeah. That was similar. Yeah. So when I bought T300. Okay. Yeah. So the another question is, sorry, I have not used TS. So is it easy? Is it easy to use TS to compare GNSS position?
Yeah, of course we must plug in some cable, and then we have to find the energy, electricity. And
no. Sorry.
Yes.
So you compare the coordinate.
Yeah, I compare
between GNSS and the TS. Okay.
Yeah, right. Yes.
Okay. So probably for surveyors it is very natural. Basically, it's very easy. And was it easy for you to use TS to compare the coordinate between GNSS and TS?
It's not easy, but the problem with TS is because we have to make correction everything. Yeah, this is not easy. Yeah, but
this is not easy. It's
it's not easy.
So we need a specialist.
It's specialist. Yes. Okay.
Okay. So the in chat only use GPS system or include other like GLONASS, Beidou system?
Yeah, everything. Yeah, Sensei. Everything is GNSS system. Yeah. Okay.
You can see chat. Yes.
Yeah.
So okay. Sorry. So do you have any questions from audience?
Yeah, please. If any other
question?
Yeah. Actually, I developed this after I got some summary training in Tumsat 2 years ago, 2019, and then I worked in low-cost GPS after that. So we also produce some product developed after the training. You are also give us lecture.
Okay, thank you.
Yeah, in the Tokyo Tumsat, I think, yes.
Tumsat. Okay.
Yes.
So maybe we don't have additional questions.
Yeah,
So
please.
thank you so much for your presentation.
Yes, thank you. Yes.
Thank you. Yes. Okay, the next speaker is Mr. Kayut Kalo M. Hong from Chulalongkorn University.
Yes,
So,
I'm here.
Okay,
right
thank you for joining. So please, could you start your
now.
presentation?
All right. Yeah.
Thank you.
Okay. Thank you to Professor Nobuki, and good evening to everyone. Today, I would like to present our research results about the performance assessments of the mean atmospheric temperatures, which is derived from ARS and AR5 products for serious water vapor in Thai regions. And so nowadays I'm sorry, my room is close to the construction site. You may hear some weird noise. I'm sorry about that. So nowadays, many countries has been established GNSS core stations for a variety of service, such as control networks, urban planning, construction surveys, precise farming, and also applications in weather forecasting. So in this research, we are focusing on using GPS or GNSS signal delays for estimating the precipitable water vapors or the PWVs. So we can use it for supporting weather forecasting, climate change, or etc. So in order to get a high accuracy of serious water vapors, the mean temperatures, it is important parameters to convert GPS data to the water vapors, especially in tropical zones or in the middle latitudes. So the TM value is functions of the partial pressure and temperature at height. So the terminal value is usually calculated from meteorological instruments such as radio or sound profiles, which is quite expensive and is not available as most GNSS station in Thailand and also in other areas. So the alternative ways to estimate the TM value is to use the empirical models of the linear functions between TMs and TS, which is commonly used method to estimate the TM value. So in this research, the linear functions of T mean and surface temperature is used in our research. So the T mean value has been developed by many researchers since 1992 by Beris, and until now, many researchers are still continually developed and improving the new TM or T-mean models to be more accurate. In our regions or in Thailand, our first investigations of the T-mean model is started in 2016 by Suwantong and research team. And at that time, AIRS and AMSU version 6 products was used in the research. And the only capital city area of Thailand was investigated. But in this research, we will investigate the whole countries from multiple data sources with longer time periods. And this is the data we use in this research. The data on the left-hand side is data that we use to create the T-mean models. And the first data is AIRS products. It is one of several instrument systems on board the NASA Alpha satellites. So they use this instrument to observe the verticals of the Earth's atmosphere, such as temperatures, moistures, and also water vapor profiles. So, and the second data is EAR5 products. Is a new upgrade product from European Center of Middle Range Weather Forecasting, or the short name is ECMWF. And the data on the right-hand side is the data that we use to assess the performance of the T-mean model derived in this research with surface temperature from weather stations and the T-mean models from this both data sources. So in this research, GNSS data will process by GPX to estimate the Zenith wave delay, and this Zenith wave delay will convert to GIS water vapor using surface temperature and T-mean models developed or derived in this research. So this is how the data look like. So the first data is AIS products. This is directly measurements from the satellites. The satellite is orbits past to Thailand twice a day at daytime and nighttime. So this product is not cover the whole country of Thailand every time they pass to our country. So we don't get a lot of data from these products. And from for the ERA5 products, is cover the whole world, and we can get this data every hour. Is combined from many observations data, and is used as one modeling to generate this data. And the last data is GNSS core station. So we use 26 core stations around the country to assess the performance of the T-mean model derived from these two data sources. And this is equations that we use to calculate the TM values. And all of these parameters we can obtain it from these two data sources. So this is example of T-mean values and surface temperature from Ayutthaya stations. We get it from data from these data sources. So the brown dots is T-mean values calculated from equations from previous slides, and the green dot is the surface temperatures. So we can directly obtain it from these data sources. And after we have the TM value and surface temperatures, so we can create the linear regression so that we can determine the linear coefficients alpha and the beta. So in this picture, the solid line show the correlations between T-means and TS, which is not very strong correlations, but it's not really weak. So which is commonly found in these regions, and this is characteristics of T-mean and TS in our regions. And the picture on the right-hand side show the residual distributions between observations data and prediction lines. So the loose mean square is about 2.5 Kelvin for the AIS products and 1.9 Kelvin for the ERS products. Yeah, sorry, ER5 products. So distribution from the linear fitting can be reduced the accuracy of sweet water vapors when we use these linear functions between TM and TS to calculate the sweet water vapors. And this is the result of our linear fitting. So the first three model is the model that we derive in our region. So this is a T-mean model from ARS products, and this is from ER5 products. And this is a previous research from Suwantong products. And these three models is global T-mean models is a well-known T-mean model used in many research. So we would like to compare all of these T-mean models to see which models can give us the good results. So this is so in order to assess the performance of all of the T-mean models we use in this research, GPS observations in 2021 from 76 stations around the countries is used to assess the T-mean models for GPS water vapor calculations. And GPS observations, we use DeepCX to process the data to estimate the signal delays using PEP techniques. So this is our results. In this research, we use AIRS products. Water vapor is used as the reference data, and this is show the statistics results of our research. So the difference between reference data and GPS data use of the water vapor derived from all of these models. So the results show that when we use the model that derived in our regions, the mean bias is reduced when we compare to the global models. And also in this research, we would like to compare the surface temperature derived or obtained from Western station that's close to GNSS stations and the surface temperatures obtained from empirical models from global pressure and temperature version 3. So we want to compare this because some stations or some GNSS stations in Thailand maybe not have the Western stations close to the station. So alternative way is to use empirical model. So the results show that it still gives us a good result. So in case we don't have surface temperatures as GNSS station, so the global pressure and temperature version 3 is still a good, it's a good product. It's a good empirical to use to estimate the GNSS water vapors. And also we do the hypothesis testings to assess the mean bias of the different GNSS, which is derived from different T-mean models. So from our testings, the local model derived in this research show the significant improve over the global models. And it means that it is better to use the local T-mean model derived in our region to calculate the GPS water vapors. And we also assess the mean bias of these three models. The results show that there are no significant difference between these three models. So it means we can use each one of these models to calculate the GPS water vapor in our regions. Even though the mean bias of different GPS water vapor is pretty much close to zero, but the loose mean square is still high. It's about 2.7 millimeters or about 8 millimeters at 99.7% confidence. So in picture on the right hand side show the different GPS water vapor from all stations using T-mean models derived on this research. So we can see some systematic error left in our results. So this is a seasonal variations. It happened because we use linear functions of Tm and Ts without consider the seasonal or seasonal variation in our region. So we need to adjust the models to correct this semantic errors in our further research. And so this picture shows the mean bias of the different GPS water vapors from 26 stations. So most of water vapors mean bias from 76 stations is less than 1 millimeters, but there are some stations, about 12 stations, that the difference of GS water vapors mean bias is over than 1 millimeters. So it means that the local means model we develop in this research or in our regions may not fit well in every area. And this is how the water vapors time series in 2021 derived from GIS water vapor using mean models or T-mean models derived in our regions. So in Thai areas, we have three seasons: hot seasons, rain season, and dry seasons. Right now, we are in the hot seasons, and in these seasons, the water vapor is increasing until May, and then the season is changed to the rain seasons. So the summary and conclusions. So in this research, we assess the performance of the T-mean models that derived by using the data in our areas from AARS and EIM products for GIS water vapor calculations. The results show that the mean models derived, the mean temperature model derived in our areas perform better than the global T-mean models. And when the local T-mean models are used to determine the GIS water vapors, the mean bias is reduced. But even though the mean bias of the different GIS water vapors is pretty close to zero, the loose mean square is still high. And the simple linear relationships between TM and TS we derive in this research is easy to implement and distribution to other research, but it may be not fit well in every areas. And also, we found that the results of the different GIS water vapors in our when we use the linear regressions of TM and TS, it shows seasonal variation. So to describe the seasonal variations in the different GIS water vapors, the linear functions of the T-mean model derived in this research is considered to be revised or to improve to collect the variations in our results. And also the EAR5 product that we use in this research has a great potential to derive T-mean models and conduct the climate research. So in our future research, we are focusing on decrease the loose mean square of the residual distributions and also the seasonal variations in GIS water vapors calculations. So this is all my presentation today. Thank you very much.
Thank you very much. Thank you very much for very detailed assessment of mean tropospheric temperature. So yeah, amazing, yes. So do you have any questions for Mr. Kayat? So we have time because we only have 6 speakers in this session. So okay, so I have sorry, I am not so familiar with tropospheric model, but anyway, I hope I understand your presentation. So did you use AIRS and the ECM is a kind of a geo network in
Oh, it is
Thailand?
it is a free products from websites. We can download it, and it is all of the data is about the data from the atmosphere. Mostly all the data is about temperature, pressures, carbon dioxide, or something like that. So yeah, we use this
Sorry,
data.
This is not related to Thailand, over the world, in the world.
Yeah, you're right.
Okay,
Yeah.
sorry.
Yeah.
Okay.
But,
Yes,
but
anyway.
we just select some data that's cover the Thailand. So
yeah. So you showed that the local TM model in Thailand,
yeah, right,
was better than the global model.
yeah, right. Most research do this, and the results are the same. So it means when we try to create our own models by using the data in our area, the result is quite better than the global models.
Yeah. Maybe we can understand it because local model it's very close. How can I say? It's much more accurate.
Yeah, right.
In terms of maybe, yeah. So anyway, so how many base stations did you use for this?
So yeah, in this research, we select only 26 GNSS core station to test
26.
the model.
Yeah, 26.
Yeah, right. But right now in Thailand, we have about 250 stations, I think.
Oh, really?
Yeah.
So sorry, 250 stations controlled by government.
Yes, right. From
okay.
Department of Land and from the department in Thailand. Yes.
So is it free? Is it freely can be used for any researchers or people in Thailand?
Yeah, right.
You can use 250. Yeah. Oh, okay.
We ask them for the data. So
even from Japan, we can access.
I'm not so sure, but you can try things.
Yeah. But I don't know the Thai language.
You can contact Professor Chon if you want the data. So
yes. Sorry. So do you have any questions from audience? Yeah, maybe no. Okay. Thank you very much for your presentation. So
thank you.
Yeah, it is very impressive for me. Yes. Thank you. So now let's move on to the next speaker. Mr. Bing from Hanoi University of Science and Technology. Can you hear me?
Yes, I can hear.
Okay.
Hello. Yeah.
Hello.
From outside, my colleague Dr. Hiren will present on behalf of my research team.
Okay, so could you start
hello,
now?
Everyone.
Yeah.
Yes,
okay.
Yes.
Hello, everyone. Can you hear me?
Hello. Yes.
Can you hear me?
I can hear you. Yes.
Okay, I can show my slide. Okay, can you see my slide?
I can see your slide.
Okay. Okay, now we start. Okay, I'm here. I'm from Navy Center. I would like. I would like to present the GNSS spoofing detection algorithm based on a linear regression model of the phase double clarified difference. My presentation includes the following sessions. The first is the GNSS application, and the second is the GNSS radio frequency difference. The third is a spoofing detection approach, and then a linear regression model of the phase double difference to detect intermediate spoofing. And then it's the experimental result, and the last is conclusion. The GNSS system provides the precise location and precise time. Therefore, there are many applications that use GNSS to synchronize time or determine locations, such as banking system, internet system, power grid system, vehicle checking system, and so on. The application need high accuracy and reliability from GNSS. However, the signal from satellite to receiver must throughout a hard environment such as throughout the ionosphere, troposphere, and the effect by reflected signal and radio electronic magnetic system, and so on. There are factors that reduce the accuracy and reliability of GNSS. GNSS has the vulnerabilities that are low signal power and the wide bandwidth, so GNSS receivers are extremely vulnerable. The type of interference affecting GNSS signal quality can be divided into two types: the intentional interference and unintentional interference. A type of intentional interference can be mentioned as ionosphere, troposphere, and Wi-Fi signal transmission. The intentional considers the two main types, which are jamming attack using devices that transmit high-power signals, make the receiver unable to calculate the location, position, time. Two is the spoofing attack using device transmit fake satellite signal. Spoofing is the most dangerous type of the attack because the spoof transmits fake signals similar to the satellite signal structure, but the information needed for the calculation is the spoof to fool the receivers. The receiver gives the false alarm, which reduces the reliability and accuracy of GNSS. So the work focused on the method of detect spoofing signal. There are three types of spoofing attacks. The first is the simplistic scenario, use a commercial signal simulator. The second is the intermediate scenario, use the receiver beyond spoofing the receiver to collect satellite from then modify the content of the satellite information and use the spoof transmitter to retransmit the satellite signals. The third is a sophisticated attack system, consists the group of receivers and transmitters synchronized with each other and attack from multiple directions. And there are three main methods of the spoofing detection. Method one is the cryptographic, method two is the intentional verification, and method three is the signal feature. The cryptographic and the internal verification is difficult to implement or increase the code and the size of the receiver. The method of the estimating angle prior of the signal can be performed on the commercial receiver. The method is quite simple, low code, and high performance. And our work is beyond the angle prior estimation to detect spoofing signal. About the angle prior estimation method, beyond the assumptions that the authentic signal are emitted from different satellites, so the angle prior is different. The spoof signal are emitted from the single antenna, then they share the common angle prior. There are two methods of determining the angle prior: either estimation the angle prior value and estimation different angle prior signal. The method of estimating the angle prior usually use the software-defined receiver that set the high precise clock and must know the position antenna. The method of estimate different of angle prior comparing difference between the angle prior of signal can be developed on the independent commercial receiver. There is no need to set the common precise clock. If it works, we use the different angle prior method using two commercial receivers to detect spoofing signal. View of the two commercial receiver and two antenna, and we set up the system as shown on slide. You can see here. Because distance from the satellite to receiver very less, we can consider the signal from the satellite to antenna is around. The distance D of the two antenna is known. We need to find the alpha angle. To better understand the detection algorithm, we model the method mathematics as follows. The first equation is the carrier phase measurement, where you including information such as the distance from satellite to receiver, the integer ambiguity, the satellite clock error, the receiving clock error, the noise on the receiver, atmospheric, tropospheric delay, and environmental error. When performing the single carrier phase difference and double carrier phase difference of the second equation and the third equation, we can eliminate the delay, atmosphere, the troposphere, and clock error. The remaining component are the angle of arrival of the two satellite and the integer ambiguity. And we use the rounding function to eliminate the integer ambiguity. Okay, now we build the intermediate spoofing scenario. Indicate the receiver receive the signal from real satellite, the authentic satellite, and spoofer. To detect the intermediate spoofing attack, we propose method DQ. The DQ method is based on the double carrier difference method. In the DQ, we group satellite into subgroup to separate spoof signal and real signal by the decision threshold. DQ, but DQ has some limitation. Where the double carrier difference of the authentic signal cross the double carrier difference of the spoof signal. In comparison, the authentic signal either detects either temples trace leading the false alarm. Therefore, we propose the linear regression model of the double carrier difference to check the slope and deviation of the phase double difference. You can see the false alarm. The method we use a linear approximation. Instead of using different measures, we divide the data into frames. In each frame, we linear the double carrier into linear equation, and based on the slope A and deviation B to determine the spoof signal or authentic signal, and compare the slope A and deviation B to determine the spoofing. You can see here. And compare the performance with DQ from the figure from experiments result, so that the linear approximation method has much higher accuracy than DQ method. However, this method is a high complexity than DQ. And the conclusion, spoofing is a pernicious type of intentional interference. The spoof signals share the same angle driver. A more robust approach to improve detect the spoof using linear regression is proposed. These methods still leverage the concept of the angle private and require multiple antennas. However, this method has a higher complexity than DQ. Okay. Thank you for the attention.
Thank you. Thank you so much for your presentation. Yeah, it was interesting for me. Yeah,
okay.
Because we are doing the very similar. Yeah,
yeah.
Prior now. Yes, yes. Thank you. So I have one question. So, did you use SDR for this test? SDR?
No, we use the commercial receiver.
Commercial receiver.
The commercial. We don't need the accuracy clock.
Okay. Okay.
Yeah.
So
Yeah, Kubo, I can provide some extra information.
Yes.
We actually don't use the SDR here. We actually compute the model based on the raw measurement from the commercial receiver. Yeah, so we don't need to perform the computation inside the tracking or the application space, but we use the raw measurement.
Yeah. Because all you need is just a carrier phase measurement.
Yes.
All you need.
Use the carrier phase measurement.
And oscillator is the same for two receivers. So oscillator is even TCXO, okay, OCXO, TCXO.
Yeah.
Did you input the oscillator?
Oh no, we don't need oscillator. Without yeah, we don't need. We only use two commercial and two antenna.
Okay.
Independent. So, yeah. So we calculate the double carrier phase difference, the different carrier phase of the two receiver.
Oh.
Yeah. We don't need.
You don't need to synchronize. Yeah. You don't need to synchronize two receivers. Yeah. Oh, okay.
We do not need the time of the GNSS.
Yeah. Yes. Yeah. I have. Yes. Similar presentation. Okay. Anyway, so do you have any questions from audience?
Yes, I'm having a question.
Yes.
My name is John from Chulalongkorn University.
Okay.
The author mentioned that you are using the double difference to derive the angle of arrival, right? In order to detect the spoofer. And you also did some experiment to prove that if you have one spoofer, it means that all the signal come from the same direction. What if in the real case you have two spoofers in a different direction? Would this algorithm work?
Sorry?
Well?
Could you repeat, please?
Maybe two spoofer. Two spoofer.
Two spoofer. No, and now my method is only one spoofer.
So this is just only the initial.
That one. This algorithms only to detect one spoofer.
Okay.
Yeah.
One spoofer. Okay, so even one spoofer, so it is important to detect. Okay, and I have another question about. So did you test on site? Did you use a simulator or on site?
Yeah.
On site. How did you transmit of the spoofing signal?
Actually, we have to collect we have to view the satellite in the outside, the authentic satellite, and we only transmit the satellite number in the lead of the satellite in the sky.
Okay. So is it allowed for you to transmit artificial signal GNSS?
Yes.
Actually, inside our campus, we can do that.
You can do that. Oh.
Yeah.
In Japan, it is very prohibited.
Obviously, it is also prohibited here,
yes.
But for research purpose and for short time, we can do that. Unofficially, yeah.
So could you tell me how power was the transmitters? power of the transmitters?
The power is
Yeah.
the similar the authentic satellite.
Ah, very low.
Yeah.
Very low. Okay. I see.
But the return from spoof, not so fast, so we can spoof the receiver. Yeah.
Okay. So do you have any questions from audience? So okay. So you mentioned D3. D3 means 3 satellite. Sorry, maybe I misunderstood. You mentioned about D3 spoofing. D3.
DQ. Yeah.
D3 spoofing. D3 detector. Sorry.
Yeah, D3 detector. Yeah.
Yeah. 3 means 3 satellite. No.
No, with not 3 satellite.
Well, what does it?
D3? What does D3 is? You can see single character difference.
W.
And the double character is
yeah.
Then we compare the DD of the satellite.
Okay.
My English name is the DQ. D3.
Okay.
Yeah, it's actually the difference of double difference.
Yeah.
Different of double difference.
Yeah.
Okay. Sorry. Yes. Yeah, probably audience understand. Yes. Only me, I misunderstood. So should be 0 from spoofer attack. So your these 3 detectors can detect because 0 from spoofer.
Sorry.
Yeah, could you show us
Right.
your slide of the double difference results?
Yeah, the double difference.
Should be 0.
The difference of the double difference.
That's the difference.
Difference of the double difference should be 0 from spoofer.
Yes, should be 0.
Yeah. Everyone, probably everyone understands.
Because the angle driver is similar.
Yes. Okay, sorry. Only me ask you. So, do you have any questions from audience? If not, we can finish this sessions. Okay, if not, thank you so much for your presentation, Dr. Hayan.
Okay, thank you.
Thank you very much.
Okay,
thank you very much. So, okay, thank you very much for joining this session. So I'd like to thank you both the speakers and the audience for providing a lot of interesting discussions. It covers from firstly Open PPP-RTK service in Japan and Thailand, and the recent advances of GeoNet, which is a dense GNSS course network in Japan. And next is low-cost GNSS receiver performance in Indonesia. Yeah, he used to GNSS and TS. He compared, yes. And performance assessment of very science topic. So performance assessment of mean tropospheric temperature models derived from AIRS and ISH-MW. And the last one is the linear regression model of the phase double difference to improve the D3 spoofing detection algorithm. Okay, yeah, thank you very much for your joining. So this session is now closed. Thank you so much.
Thank you.